Hi everyone. We're going to revisit the issue of symmetry in section 1.7, in particular, the symmetry of even and odd functions. Let's go back to section 1.3, where we introduced even and odd functions, when we studied basic graphs and symmetry. We looked at the squaring function given by y equals x squared. And this was an even function. We assumed that the domain was the implied domain of all real numbers. The domain of f was assumed to be all real numbers. Remember, in order for a function to be even or odd, the domain must be symmetric about 0. R itself is symmetric about 0. Now, what was true about this squaring function? Not only was its domain symmetric about 0, but whenever we input a pair of opposite values for x, like 3 and -3, we got the same function value, the same y coordinate. In this case, 9. The square of 3 was 9, and also the square of -3 was 9. Meaning that on the graph of y equals x squared, the point 3, 9 was on the graph, which meant that the point -3, 9 was also on the graph, because f is an even function. That's a demonstration of symmetry about the y-axis. Anytime xy is on the graph, opposite xy is also on the graph. Anytime xy is on the graph, opposite x, comma y is also on the graph. A function is even, in general, if and only if you input opposite values for x, whenever x is in the domain of f, the function values are the same. F of opposite of x equals f of x for all x in the domain of f. Graphically, that means that we have symmetry about the y-axis. For every pair of opposing x values in the domain, the y values are the same. Here's a proof. We want to show that f of opposite x equals f of x. Well, when you square the opposite of x, you just get x squared, which was f of x. F of opposite x equals f of x for all x in the reals, which is symmetric about 0. So the squaring function was a basic example of an even function. By the way, constant functions are all even functions. Like, for example, the function given by f of x equals 3, that's even. X equals 2 gives 3. Also, x equals -2 gives 3, for example. The graph is symmetric about the y-axis. All constant functions are even. I don't care if 3 is an odd integer. All constant functions are even. The zero function, in fact, is both even and odd. Now, what about odd functions? Well, the identity function given by y or f of x equals x to the first, that was a basic example of an odd function that was symmetric about the origin when you graphed it. Another one we looked at was the cubing function given by f of x or y equals x to the third, or x cubed. That was a basic example of an odd function. Again, the domain is all reals. The domain is all reals. Now here, remember, the domain has to be symmetric about 0 in order for a function to be either even or odd. And why is it odd? Because when you input opposing values of x, like 3 and -3, you get opposing values for y. Positive 27 versus -27. Or, if you take more humble numbers, if you input 2 and -2, you get as the cubes, the y coordinates, 8 and -8, which are opposites. If you input opposite values of x, you get opposite values of y, opposite function values, as outputs. If 2, 8 is on the graph of an odd function, then -2, -8 must also be on the graph of an odd function. In general, if xy is a point on the graph, then for an odd function, the point opposite x, opposite y must also be a point on the graph. For example, 2, 8 and -2, -8. In general, in order for a function to be odd, whenever you input opposing values of x on the domain of f, the resulting function values are opposite. The y-coordinate at opposite x is the opposite of the y-coordinate at x. The function value at opposite x is the opposite of the function value at x. And this is indicated graphically by symmetry about the origin. If the graph is rotated 180 degrees about the origin, we get the same graph. Like for the graph of this rising snake, y equals x cubed. Rotate it 180 degrees about the origin, you get the same graph. Here's a proof. Again, if you want to prove that a function is even or odd, if you're given the rule for f of x, you want to analyze f of opposite x. When you substitute x with its opposite, this is a substitution, remember. When you substitute x with its opposite, look here, you get the cube of opposite x, which ends up being the opposite of x cubed, because the cube of -1 is -1. And that's actually the opposite of the original function rule here. F of opposite x is the opposite of f of x for all x in the reals, the domain. So now we're going to talk about even functions and odd functions more generally in section 1.7.